How are you guys doing? Doing all right?
Yes.
Anyone suffering from allergies the same as I am? No?
I am.
Yeah, it's terrible. I don't know. Not such a fun time for me this time of the year. Okay, okay, guys. Today we're going to go work on the homework mainly. We'll see if we have some time to finish up some topics that we didn't finish during the week. I have bad news and good news for you.
The bad one.
What do you want to hear first?
Bad
Okay, here the bad news. The lab report is due next week. Okay? So, the good news is that we're going to fix a limit up to a maximum of 5 pages with figures, with everything, okay? We don't want your report to be long. Actually, we, more than the writing, this is not petrophysics, we're not going to evaluate your writing. I just want to make sure that you know how to use the data, how to interpret the data to compute the things that we're asking you. That's what we want to see. You may have to add a little bit of writing to explain what's going on, or if something went in another direction in which it was not expected, and that actually happens in the laboratory. It's never that you're always going to get what you get. Then you have to explain that. Right? The writing should be pretty concise, very dry, you know, saying we measure Young modulus equal to this. That's it. Okay? Not a lot of explanation about it was hot and then my laboratory mate did a mistake and after that, no, okay? Just be very concise. Say we couldn't measure the Young modulus because of this and that, or the sample broke earlier than what we thought, so the unloading modulus is not reported. That's it. Okay? So all the labs then are going to be due the week after. And I think it's going to be better for you because as soon as you get the data, you put the plots together, write a little bit, and submit it, and that's it. And that's also needed because we need it for the midterm. You need to know the procedures to compute Young modulus, to compute strength of rocks, something that you're going to need later on to solve problems. Okay? All right, so let's talk about the homework now. For the homework that you have to start tomorrow, you have to solve 3 problems, and these are problems 3 to 5 in this list. I imagine that you're done already with problems 1 and 2, and if we have some time, I'll get back to problem 1. There's no, actually it's to another one that I'd like to discuss a few things, and if you have some questions also, just let me know. But I guess that you're almost done with this one. It wasn't too difficult. It's actually very similar to what you're doing in the laboratory, but in this case, you're using data that was obtained with another triaxial apparatus in my laboratories, which is a lot fancier than the ones you have. Okay, problem number 3. Problem number 3 is a problem of interpreting the stress and the strain tensors. So let me come back over here to the dog camera. We're going to talk about homework number 4, isotropic loading. In this case, we are seeing a type of loading which is different to what you have seen before. In isotropic loading, if we have a piece of rock, that piece of rock is being subjected to stresses which are all the same in the 3 directions. And we're going to call this one sigma iso from isotropic. Notice that this one is different to what we did before, in which, just for the sake of simplicity here, I'm just going to do it 2D, but the plot is meant to be 3D, in which we have no confining, and the sample expands to the sides. If you remember, we call this one unconfined loading, and it's also different to the one that we saw after, and we're going to see also in a little bit, in which we set boundaries here on the side that you could think as that as rollers that do not let the rock expand in the two lateral directions, but let it deform in this direction, and we call that one-dimensional strain loading. This one is different to those two. And because of that, there is going to be a different proportionality between sigma stresses and strain. So the problem is asking you to solve what are going to be the strains as a function of stresses. And if you remember, the matrix that links these two is the matrix D, which is called the compliance matrix. Okay, so here's the key. With isotropic loading, all the normal stresses, sigma 1,1, sigma 2,2, and sigma 3,3 are going to be the same and are going to be equal to this value sigma iso. And what do you think about the shear stresses with isotropic loading? Isotropic loading, you can imagine that as loading with a fluid. If you submerge something into a fluid, it's going to be subject to isotropic loading. So what do you think the shear stresses are going to be? They're going to be all zero. And again, if we make this analogy with a fluid, fluids cannot apply shear stresses, at least for a long time. So those are going to be zero. All right, so everything you have to do, I'm going to let you do this, is since these ones are zero, similar to the problem that we solved in class, we're not going to write those in the matrix. I want you to tell me what are going to be epsilon 2,2, epsilon 1,1, and epsilon 3,3 as a function of, here there's going to be a matrix which is going to be 3 by 3. And here, this is going to be sigma 1,1, sigma 2,2, and sigma 3,3, right? Instead of that, let me just go ahead and write the value of sigma 1,1, sigma 2,2, and sigma 3,3, which is this one. So fill up this matrix, make the matrix multiplication, and tell me what is the relationship between volumetric strain and isotropic stress. And remember that volumetric strain is going to be equal to the summation of all the linear strains. So I'd like that you tell me then what is the relationship between this number and that number. Okay? So let's work on that. And if you have any questions, let me know. We'll try to finish that in about 5 minutes, okay? The solution is actually in the notes, so I'm not going to give you extra points for this, but I strongly recommend that you solve the problem now, that you know how it's solved, because there are variations of these problems that I want you to learn about how to do, and they are not in the notes. Yes? Yeah. So this one is C, and has the units of pressure. And the other one, the previous one, this one is D. No, this is D. This is D. This is C. Of D. Yes. No, you cannot use, no, it's not gonna work. No, you have to work it out from the original compliance or stiffness matrix. The constraint modulus is applied just for one characteristic state of stress or loading path. But this one is a different loading path, so it's not going to work. And that's the objective of this problem, to see why it's not going to work. Yes.
So basically, this is the and the 1-1. So you just need to do, it should be the same for all three. Because the stress is the so what is it?
You only got the top of it, right? Oh.
Ignore all these. Where are you getting this?
That's the original compliance.
Yeah, and then because you have no shear stress, you cancel this there. So you're gonna be left with this matrix.
Oh, okay, because he did the triangle.
You can do that. No,
Yeah, because he gave us this. Okay. Yeah.
Yeah.
I'm right there.
Wouldn't it be this?
Or it's gonna be the other one.
Why is it the other one? Because this one is
But then,
that, and then this one is a vector, a matrix, and another vector. Oh, because we don't have any shear, right?
and then for the other one, it's practically the same thing, but then you don't have any of these terms because
Yeah.
so
That's why you get this one.
Yeah, it will be this one.
Yeah. Okay.
Yeah. Yeah, for this kind of
Yeah, here I essentially go for the isotropic by like using a matrix separation thing. I got that. And then now that I separated the terms, I can solve the volume metrics.
But my question is, so you solved this matrix for which one?
Yeah, for isotropic. So yeah, I just solved the matrix and I got.
And you did it again like, with this and this? So you get 3 equations, right?
Oh, it's gonna be like a very long one.
Oh, so you add them all together? Oh, wow. Okay.
Yeah. Yeah, I just use